Hey everybody, Thrasher here. We are going over some math topics because it's going to be important in this next unit. The first thing we're going to talk about is this idea of proportions. They're like equations, but not quite as specific. You'll see what I mean. And then we got to do a quick reminder on how to deal with scientific notation, how to write it, how to figure it out, and also how it shows up in your calculator, okay? So hopefully you're paying attention and following along because these things are important in this new physics unit. All right, so to start off with proportions, all right, when I say proportions, that's similar, but not quite the same thing as an equation. Equations show things that equal one another. For example, 5 plus 2, that is equal to 7. They are the same thing. They are equivalent. 7 is equal to 5 combined with 2. All right, here's another example of an equation or something that's equal. 1 hour is equal to 60 minutes. Nobody would debate that. These two things are equivalent. They are equal to one another. Okay, also in physics, you might not know this, but it's still true that frequency and pitch, those are the same thing in physics, or the same things. Pitch is equal to frequency. Now, proportions, on the other hand, they show that things are related to each other, all right? Not necessarily equal, but related. Here's an example. Eating donuts is, and just like you have this classic equal sign, you all know what this is, right? This is one way to represent the idea of a proportion, okay? Eating donuts is proportional. It's related. It's a relationship to Thrasher gaining weight. Now, when Mr. Thrasher eats donuts, that's not the same thing as his weight. Me eating 5 donuts, that's not equivalent to my weight, but it is certainly related. You could probably imagine if I'm eating a lot of donuts, maybe you could guess what would happen to my weight. These things are related to each other. They are proportional to each other. Likewise, we learned about Newton's second law. Oh man, throwback. Well, in that case, we learned that how much something is accelerating is related. It is proportional to how much total force. This wasn't the equation we learned, because this is not an equal idea, but these are a relationship idea. These two things are related. Okay? So again, the symbol for proportion, while you all know the symbol for equal, the symbols for proportion, they take one of two different forms. To be honest, online and in textbooks, you might see this one a little more often. I actually like this one. It's a little easier to draw or to write or to type. Okay, but you might see either one. I'm sorry, there's not one standard symbol. You might see either one. So what I had before, notice, it's that same idea. Here I use that symbol, but now I'm using the other one. It means the same thing. So donuts eaten is proportional to weight gain. So maybe I'm lazy. I don't want to write this all out. D for donuts. Weight is letter W. Now, how do you think this relationship works? Well, if I eat more and more donuts, what do you think's going to happen to my weight? Well, probably it would go up. If I ate way too many donuts, maybe I didn't change anything else, I didn't start exercising anymore. Yuck, that sounds terrible. If all I did was eat more donuts, my weight would probably go up. That's the relationship. Again, they're not equivalent to each other, but they are related to each other, all right? Sometimes, to be honest, even though it's not an equaled idea, it's not an equal equation, it's sometimes just helpful to think about it, okay? If my weight gain or my donuts eaten was 2, well, okay, maybe the weight was 2. If I increase this to 3, well, then I increase this to 3. Increase this to 10, increase that to 10. So it's a lot of similar thinking with equations, even though it's not actually technically equations. All right? Now, let's say I started eating less donuts. What would you expect would happen to my weight? Yeah, it's not a trick question. Notice I have a similar idea. Notice the same thing happens. More donuts, more weight. Less donuts, less weight. Oh, okay. Also talking about Newton's second law. If I was comparing the acceleration to the force, if I have more force, yeah, I have more acceleration. You can go a little further sometimes. Now, if I had twice as much force, it turns out, I won't do the math here, but if you had twice as much force, you'd have twice as much acceleration. Likewise, if I cut down the force, if I was pushing on something less and less, I'd have less acceleration. And sometimes there's a direct cause where if I know it's 1/5 as much, Oh, well, over here, it's 1/5 as much. But notice, similar to donuts and weight, I have the same idea. Both arrows do the same thing. If one goes up, the other goes up. If one goes down, the other goes down. I see that in both cases. This idea, this kind of relationship, when both are doing the same thing, that's known as a directly proportional relationship. They are directly related, or sometimes called linearly proportional. Sorry, again, you might see similar terms that are slightly different, directly here, linearly here, but they mean the same thing. Now, not all proportions act the same way. Here's a different scenario. Let's say I'm comparing the number of people to the price of tickets. Maybe it's going to a concert, going to a band show that you really are interested in. Okay, here's the number of people. Here's the price of the tickets. Imagine, what happens if I increase the price of a concert ticket? Let's say it went from $1 to $1,000. What do you think that would mean to the number of people who started buying tickets? Oh, it would be the opposite. If the cost of the concert goes more and more and more, the number of people probably who are going to buy those tickets is going to go down and down and down. Oh, this is different. Remember, before it was doing the same thing. This is an opposite kind of relationship. Again, sometimes it's easier just to, if this is getting weird and confusing with this weird little symbol, just think of it as an equal sign, okay? If I make the denominator of my fraction bigger and bigger, my result is in fact smaller and smaller. That's what I'm seeing right here. When the price goes up, the number goes down. If I double the price of tickets, maybe that means I have half. Oh, notice again, opposites. If I double 2 times more the cost of a ticket price, maybe I have half or 2 times less the people going. Interesting. This is known as an inverse relationship or inversely proportional. Okay? So we've just seen a couple different examples. Again, the equation, here's our example back again with Newton's second law. Here was that equation we learned, but there's a couple of proportions in there. When the force gets bigger, the acceleration gets bigger. They do the same thing. When the force gets smaller, the acceleration gets smaller. Though it's known as a proportion, this is a direct proportion, or again, linearly proportional. Or you could have the opposite, the inverse. Oh, this is an inverse relationship. If the mass of the object goes way and way bigger, imagine a ping pong ball versus a train. Well, a train is probably going to accelerate way less. It's the opposite. Here is an example of an inverse proportion, an inverse relationship. Okay? Again, if you want, maybe you just keep using an equal sign just so you're familiar. When the fraction gets bigger on the bottom, the result gets smaller. Okay, that sometimes is helpful for students. This can also show up graphically. So here, oh man, there's that other symbol. This is an example of a direct, a linear relationship. All right, let's look at our picture right here. As you get older, as your age increases, your height, oh, it increases. Both go up. When age goes up, your height goes up. Oh, okay, it's just like we saw before. Here is that same example with the price. If the price of tickets gets bigger and bigger and bigger, the number of people who buy tickets to that game probably gets smaller and smaller and smaller. And those are the same little relationships I showed before. Notice they're using a slightly different symbol here. Okay, but again, I have this fraction. So again, we have linear or direct, they do the same thing. Or we have inverse, where they do the opposite things. If you need to hit pause for a second, go ahead. So not only can we look at these things as simply both go up, both go down, but we can look at them as a graph. All right? There are other relationships. This shows a constant. If there is no relationship, if there is no proportion, it's just constant. For example, if you go to the supermarket on Monday or Tuesday or Wednesday, the price of salt is probably the same. We'll pretend we're ignoring like sales going on. But more or less, the price of salt doesn't depend on the day of the week. So there is no relationship. It's just staying the same. And in fact, there are other more complicated ones. There are square root relationships. There are quadratic relationships. We'll maybe touch upon some of these later on. But these are kind of the core 3. The linear, the same idea, both go up, both go down. Or the inverse, the opposite. Okay? That's it. That's our idea for proportions. I'm going to stop this video here. Thanks a lot for watching.